Hello students, and welcome to today's chemistry class for SS3. In today's class, we are going to be handling the topic alkanoic acids. Before we proceed, let's take a good look at our lesson objectives. At the end of the lesson, the students should be able to know the functional group of alkanoic acids, understand the naming pattern of alkanoic acids, name monosubstituted alkanoic acids, name disubstituted alkanoic acids, mention the uses of alkanoic acids. But just before we proceed, I would like to tickle your fancy a bit. Do you know why you should not drink water while reading chemistry books? It's because in chemistry, concentration reduces on addition of water. You get the drift? So, alkanoic acids are also known as carboxylic acids. A carboxylic acid can be identified from the carboxyl functional group and the oic name ending. Now, a classical example of the functional group is this. That is the COOH, the functional group for carboxylic acids. It is also written in this expanded format. Let's now take a look at the naming pattern, that is nomenclature, of alkanoic acids. The number of carbon atoms in the longest carbon atom chain containing the functional group is taken as the root hydrocarbon chain. The corresponding alkane is then named with the ending "ane" changed to oic acid. Now, let's take a good example and see what these statements mean. You can see an example here. This has only one carbon atom with the OOH. This is methanoic acid from methane. So we count the number of carbon atoms because it is just one, which is supposed to be a methane. We now change the last "ane" to oic acid. You can see here we have two carbon atoms and the OOH. So this one, instead of ethane, will now be ethanoic acid. Likewise, we are having this that has three carbon chain with the OOH. So when we name it, we are going to call it propanoic acid. Alkanoic acids are not always straight chains. They can be branched or substituted. Now, let's take a look at a few examples. You can see this branched chain alkanoic acid. It has three carbon chains as its longest continuous carbon chain containing the functional group. Now, you can see it has a substituent. That's it, the arrow is pointing at. It's the branch, and it is just one carbon atom branching away. Meaning, instead of calling it methane, we say methyl. If it were two carbon chain that branched, we're going to call it ethyl. Now, that methyl group is attached to carbon 2. Count from your right, where the COOH is. From that first C, you see that the carbon where the methyl group is attached is on carbon 2. So, if we're going to call the name of this compound, we're going to call it 2-methyl propanoic acid. Propanoic acid because it has three carbon chain as the longest carbon atom chain, and 2-methyl because the methyl group is attached to carbon 2. Let's quickly take a look at another example. You will see that in this structure, the longest continuous carbon chain is 4 carbon. So ordinarily, it should have been butanoic acid. But because it has a substituent, that is a branch, we are going to take the branch into cognition. Now, look at the branch here. That's the one carbon atom that is branching away, which I told you earlier will be a methyl group. Now, that methyl group is attached to carbon 3. If you count from the OOH towards your left, you will see that that is carbon 3. So that if we are going to call the name of this compound, it will be 3-methyl butanoic acid. In like manner, let's take a look at this other structure. You can see that the longest continuous chain counting from the OOH is 3 carbon atoms. But the 3 carbon atoms has 2 substituents. Now look at the first substituent. This substituent is attached to this carbon that the arrow is pointing at. Look at the first substituent, and then this is the second substituent. 2 substituents attached to 1 carbon atom, and that particular carbon atom is carbon 2 when you are counting from the OOH going backwards. So if we are going to call the name of this compound, it will be 2,2-dimethyl propanoic acid. 2,2 because there are 2 methyl groups attached to carbon 2. So on carbon 2 there's a methyl group, on the same carbon 2 there's another methyl group. So we say 2,2-dimethyl because it's now 2 methyl groups. Propanoic acid. Propanoic because there are 3 carbon atom chains in the longest continuous carbon chain. Please note that in all these compounds we just named now, you will notice that between numbers we put a comma to separate it, and between a number and an alphabet we put a hyphen to separate, and you write those names as one word without space, no matter how long the name is going to be. All these are part of IUPAC rules or nomenclature of naming alkanoic acids. Examples of other alkanoic acids include pentanoic acid, heptanoic acid, nonanoic acid, hexanoic acid, octanoic acid, citric acid, and lactic acid. You would remember that citric acid is from fruits, while lactic acid is from milk. It's now time we take a look at the preparation of alkanoic acids, but we're going to use ethanoic acid to represent the family. Now, the complete oxidation of ethanol to ethanoic acid by acidified sodium heptaoxochromate 6 solution is what we are going to use. Now, ethanol undergoes oxidation first to ethanal and then to ethanoic acid. This is the reaction. You will notice that first this is ethanol. It's going to react. These are the reagents to give us ethanol, and then ethanol will go on to give us ethanoic acid. There are other ways of preparing alkanoic acids. These other ways include distilling anhydrous sodium ethanoate, that is CH3COONA, with concentrated H2SO4. Now that is the equation of reaction. You can see CH3COONA plus H2SO4, that will give us CH3COOH, which is the alkanoic acid, plus NaHSO4. Again, we can use the boiling of methyl cyanide, CH3CN, with an acid. This is the equation of reaction: CH3CN plus HCl to give us CH3COOH plus ANH4Cl. Let's go on to now look at the physical properties of ethanoic acids. Ethanoic acid is usually a colorless liquid with a characteristic sharp and pungent smell. Also, it is soluble in water, and a dilute solution has the usual sour taste of all acids. It turns blue litmus paper red. Of course, it is an acid, so it will do that. It has a boiling point of 118 degrees Celsius. The chemical properties of alkanoic acids. Alkanoic acids are weak acids. The acid dissociation constant, Ka, is very, very small. They have all properties of acids, like liberating hydrogen when reacting with metals and liberating CO2 when reacting with triisocarbonates 4. They undergo esterification. Remember, that's the forming of esters. Reaction of an alkanoic acid plus an alkanol will always give us an ester and water. Let's now move on and check out the uses of alkanoic acids. Alkanoic acids are used as solvents. Also, they can be used in food industries as vinegar for preserving and flavoring food. They can also be used in the manufacture of cellulose ethanoate, which is used for making synthetic fibers such as rayon. Alkanoic acids are also used in making compounds like ethyl ethanoate, ethanoic anhydride, which is used in making aspirin, cellulose ethanoate, used for packing, that's packaging materials, propanone, etc. Time now to take a quick summary of everything we have learned. In this lesson, we learned about alkanoic acids, the physical and chemical properties of alkanoic acids. We equally learned about the IUPAC naming or nomenclature of alkanoic acids. We learned about the uses of alkanoic acids. Let's now take a quick assessment to see how far we have studied in this class. Question 1. Ethanoic acid is usually a colorless liquid with a characteristic sharp and dash smell. A. Pungent. B. Annoying. C. Foul. D. Dirty. Esters are produced in a condensation reaction between an alkanoic acid and an alkanol, known as A. Polymerization, B. Esterification, C. Dehydration, D. Hydrolysis. And so, with this, dear students, we have come to the end of today's class. Thanks for watching, and see you in the next lesson.